All right, we have two presenters for our third session. The first one is Romeo. I'm gonna.
Ciupeca.
Thank you. I didn't. So, Romeo is the president of Greencraft LLC, which is using innovative engineering to lead the way to the next generation of high-performance concrete construction with industry-shaping technology and a deep sense of environmental responsibility. Greencraft's new insulated concrete products and accelerated concrete curing and concrete forming methods evoke the true meaning of green technology. Romeo will be accompanied by Neil. Unfortunately, I don't have a bio on Neil, but you can talk about yourself a little bit when you get up. So thanks, Neil.
Hello, everybody. I'm very much appreciating being here to talk about this new material. It's novel. Basically, first of all, what is hyaloclastite? Hyaloclastite is basically Greek from meaning broken glass. And this broken glass is produced by lava erupting under the water. And it's sort of like nature making slag cement. Lava, high temperature, if it erupts underwater, shatters and it quenches, it arrests development of crystal. Under a subaerial eruption, lava cools slowly and you have different layers of lava as it cools down, and it becomes crystalline as it cools over time. A lava eruption underwater can take place in a body of water, like a lake, or during the last glaciation under the ice shield. Eruptions that would take place under the bottom of the ice shield would melt the ice, creating a pool of water, and in that pool of water, there are different layers of size of lava, from pillows to breccia and hyaloclastite. Depending on the amount of these, on the size of these formations and the volume of the eruption, certain parts of a formation like this would be suitable for what we're talking about here. Here in the U.S., at the bottom of Lake Bonneville, 16,000 years ago, we had an eruption that also came through a number of aquifers. And in this eruption, if you can imagine, that is like nozzles injecting cold water into this flow of lava, meaning that the water mixes with lava, creates steam. That's an expansive force. It accelerates, the eruption and pre-quenches this lava. And when it hits the bottom of that lake, everything pulverizes in very fine sand-like glass, okay? So we've taken this material and ground it up in a fine particle, in this case 4 micron, 8, 12, 16, to see different properties. I'm going to talk about this thing first. This is some mortar cube ASTM 618 using type 2.5 Mitsubishi cement from the Cushionberry, California plant. And here we did some the 4, 8, and 12 micron D50 side by side with the fly ash and the Metakaolin from BSF. And what we generally have with this material, it is low water demand. Sometimes, some of the tests come up to be neutral, some come up to be slightly larger. And it is the properties of this material. It is a basaltic lava chemistry. Which means it's low silica, but it has a lot of other things in it. High silica volcanics are hydrophilic, and low silica volcanics are hydrophobic. In here, we were trying to determine, hey, what would be the optimal size to have a fly ash like from a reactivity point of view. And we determined that to be around 12 micron D50. These are, those results plotted. So this is some other evaluation done by other people. Here we have ASTM 618 certification. It's a little blurry because we have both the 4 micron and the 8 micron side by side. But this is 48.7% silica, about 13 point something aluminum, and 12.7 iron oxide with a general sum of about 75% of the 3 oxides. And in the alkali, this is a low alkali. In this particular case, it's below 2. Similar product from Iceland, it is below 1. We have done a lot of research with the materials from Iceland. I'm going to let Dr. Berg come up here and talk about the research that we have conducted with Turney Consultant.
Okay, so we're basically, a lot of the work I do is related to durability and sustainability, and so we're trying to do some testing to see how can this enhance the properties of the concrete. So it's a little bit different than this meeting the specification to be to replace the 618. It doesn't do more than that. And so we did a fair amount of testing. Of course, we looked for ASR behavior, and can you air entrain it? Because at least in the North America, a lot of the concrete sees freezing and thawing temperatures. So we might make sure for that. The strength was always important. Then we looked at transport type properties like conductivity, non-steady state diffusion, bulk diffusion, capillary absorption, and freezing and thawing. And we could take all this information and do service life analysis as to how long a structure built with this would last. It actually shows some major improvements. We also did some isothermal calorimetry to get some idea of why we're getting the better performance. Here we go. So anyway, the various mixes we looked, we had a control mix. These were all at a 0.38 water cement ratio, I believe, and they looked at, it was basically a durable mix, and we looked at fly ash, silica fume, metakaolin, fly ash at a higher level, and the product, particular product at 0.4 microns and 8 microns. And we looked at anywhere from 25 to 20% replacements. The linear, we did shrinkage because that's important. They really have to crack. You can see that in this particular mortar bar expansion for 1260, 1567, and a very reactive aggregate, these materials did very well and actually did better than silica fume at and a higher amount of fly ash at a 28-day running it. So these are very good for ASR, and they compete very well with some of the known actors that are used for that. For the concrete mixes, matter of fact, the last stuff was done at the standard ASR test water cement ratios. The concrete was done at a lower water cement ratio. These are durable concretes. Mixes like this are used on some monumental bridges, maybe a little bit less water, in some case, water cement ratio, cementitious ratio sometimes lower. But this is like the ballpark to get in that you need to do, and we're going to use this later on. We'll show you for modeling. You can see that you get a cement reduction, obviously, when you add all these materials to it. So that's very good from that point of view. And you can see just so much reduced. And these are relatively low cement contents compared to what often can end up in high performance concretes. And we go through the various, you see the water content's also very low, and these are basic designs. And I feel the bottom thing is admixtures we had to use. So in order to get the same amount of slump, it was basically
less, you know, was right along the line with other materials. So it's
Basically good, good performance on that end. So the plastic properties,
we can see that we actually had more slump on some of these compared to Silica Fume, Metakaolin for sure, and in this case, better than fly ash and Silica Fume, and then the same thing comes along. One of the things is you have to workable concrete. So this is, you know, from the point of view of the engineering design, you want the people to make it. You see the setting time, unlike fly ash, is closer to controlled values, so it doesn't retard as much as a fly ash mix. Mechanical properties, we received very good strengths. Looking at it, you can see longer times, and they keep getting better, and they're better with the Silica Fume and equivalent with the Metakaolin, especially at longer times. So we had very good good strength on this, and and one thing we look later on, these things are still getting better in time. So you can see the strength data, and the best one ending up being one of the ones we're looking at, and Metakaolin in this case was pretty good, and some of these other ones. So you can see we got very good strength development, and so a lot better than what you get with fly ash. Freezing and thawing, they did very well. They all passed freeze-thaw tests, which is good. And transport properties, which we looked at over long periods of time, not just 28 or 90 days. We went all the way out, went out there. You can't see it on that other one. Over like 600 days or so, or 900. And we can see we're looking at conductivity, which is directly related to permeability. You can see that we have low values, relatively low values up front because of the control and fly ash, a little bit higher than the Silica Fume and Metakaolin, but by the time we get down to longer times, we're much lower than the Metakaolin and the Silica Fume. And the fly ash, of course, has come down in time as it gets better. So we're basically showing that this stuff continues to hydrate and it gets better. Initial diffusion coefficients we can look at, they're also set up a little bit higher, and then the better the fly ash, and then eventually came down also. And the bulk diffusion, you can see 2 to 3.9, and fly ash is higher as expected. And these were lower here, but they came down in time. Water permeability, capillary pore permeability is also absorption is also reduced with these materials. So they did, so basically, from the point of view of transport properties which are needed for corrosion modeling, they're giving a large benefit. We did look at these look at some of the conductivity over time as an idea of how the concrete is going to get better. So you have a typical control curve, very slow decrease in what we would call an aging coefficient. And these other ones, fly ash starts up here, it comes down, so but these also have low slopes. The Metakaolin and Silica Fume were practically flat. So they don't get much better in time, but these materials are getting much better in time. So how do you use this? Well, one way to look is how long would a bridge deck, corrosion bridge deck. So we used Salt Lake City as a severe example. We want a 3-inch concrete cover over the deck, or 75 millimeters, and we use Live 365, but we modified the defaults in 365 to relate to the data that we have as far as end values have, and also the absorption and the chloride buildup. So we based the diffusion coefficients on 15.856, which is the bulk diffusion, and then the surface buildups were corrected to take account to the fact that there were just estimates in the 365 program. So it's a good program to use if you want to compare things. But if you want to get down to actually modeling it, you have to start really playing around with the defaults. So we look at predicted times to corrosion initiation. You can see that the best times out here are the PVTs. They're out over here. They went far out, and you can see here's the control, and you can look at the date times. Even the Silica and the Metakaolin, because they don't get much better. They'll be better than the control in this. but they don't get you out to a 100-year design life that you might be looking for.
Normally, to compensate for that, we might use a more corrosion-resistant rebar or add inhibitors or something. But at least it's conceivable in the model here that these materials, because they do get better in time and start low, they can give some good performance. What the isothermal calorimetry results. So if you want to use this in a mass concrete, you can see for fly ash, you can see a reduction in the total amount of heat that's put out. For
these other ones, you can see not quite as good at fly ash, but almost in the same neighborhood. Silica fume's a little bit less under control, but not as large a reduction. But the Metakaolin is kind of interesting. Based on these results and this Metakaolin, I would advise using that one in mass concrete, thinking that you're replacing cement and you're going to get a reduction in your heat output. You can see that's actually fairly high per gram of cement. It's a little bit lower, the silica fume is a little bit lower, and you can see on these other ones. Yeah, no reason it's lower per gram of cement, but there's more cement on the silica fume case. And these are really blown up scales, so the silica fume looks like this is instantaneous heat in the early days. It looks a lot lower, but the scale is blown up to separate the two, and you can see the Metakaolin ends up being pretty high up on the top there, and the other ones are better than the cement and still give you your a lot of heat coming off. So increase the clinker placement ratio, increase the overall CO2. And the mineral deposit doesn't have its initial CO2 footprint is zero. There is some cost on getting it to market and grinding it, but estimated to less than $100 a kiloton, 100 kilotons per ton compared to 700 to 800 for OPC.
And I did work on ACBMs and on alternative cementitious materials. They're really not low carbon. They're lower carbon than cement, but they still have carbon footprint in grinding them, making them. So it's a misnomer to think that the materials that are commonly used now are zero carbon. There's still carbon associated with them.
A little bit about me. Remember, I'm a fellow at STM and ACI and corrosion group. And I'm a vice president of attorney consulting group, and I do a lot of work in all these societies as far as trying to get standards and specifications related to durability of concrete, whether it be related to corrosion, chemical resistance, or dimensional stability. And I think on that end, I can say thank you.
Thank you. Anybody have any questions?
Can you explain a little bit about the method of grinding and how did you use a particle size analyzer to differentiate between these two after you grind down the material, and how do you account for the extra energy that is required to prepare this new materials as a whole? The energy consumption process.
The grinding process, we have process using vertical roller mills. We have process using ball mills with different diameter to length ratios. So it is a standard grinding process, if you will. The classifying to get to that particle size would be a standard classifying process. In this case, it was, a cyclone with a classification, air classification. I'm not sure on your question of the energy. I don't know that I understood the question.
I was just mentioning, how do you account for the total energy of the system? If you do that work later on, you have to account the energy that is required for grinding these materials, right?
Right. So we said as far as the CO2 impact, this is a natural product in a fine particle size. We estimate that the mining process, it is so efficient, it is literally like scooping up sand at the beach and throw it in the back of a truck to take it to a processing plant. So that may account for about 7 to 8, kilogram per ton of the mining, harvesting process. Then the grinding process is electricity powered, and that we said is a function of what type of, what's the carbon footprint of that electricity being used. This mine in Utah is in an area with huge development of solar and wind. So it's hard to say right now, is that a 30, 40, 50, 60? I mean, we still have a coal power plant up the road, so in the worst case scenario. So literally that's the function of what is the carbon footprint of that kilowatt hour that we're using to grind this material with. And from that point on is, transportation to market.